Another really popular question we often get asked is, how do you go about popping a balloon or a bubble? Basically, how do you disable a pressure constraint as soon as my cloth tears? So let's talk through this. I'm going to start off with dropping down a sphere, diving in there. And in this case, I want to take my sphere, turn it into a polygon with a frequency of, say, 16. And in this case, I scaled this down a lot, like 0.02. Let's reframe this. Now I want to pre-break this to form individual pieces, which we can then weld together and break. And this mesh is a bit too regular for my taste, so I'll use a remesher, set to a fixed length of 0.003, and I'll run this 8 iterations. These are values that just came out of trial and error with the previous test setup that I built, and they worked fine, resulting in such a mesh. Next, I'll drop down the edge fracture node to fracture this sphere geometry here, highlight it, set my initial pieces to 36, so this will be fractured into 36 individual pieces. Now let's configure our vellum constraints using a vellum cloth, and I will just reduce the thickness of this one to 0.0005, so really tiny particles here. Let's just scroll down. Also, as this thing expands like a balloon, I want to dial back the stiffness to a low value, like 5, and increase the damping ratio a bit, like 0.33. Again, numbers that I found out by trial and error using a previous test setup. Let's disable compression stiffness, and also scale back the rest length scale so the thing contracts if there's nothing counteracting. Let's just quickly check for the bend constraints. Yeah, I want to dial back the stiffness here to 0.01, and that's about it for that. Next, let's weld those individual pieces together using a vellum weld constraint. And again, let's go over the settings. That looks right. And in here, I want to check the output group and call this one weld bend. So all my newly created weld constraints will rest in that group called weld bend. Also, let's enable the braking so that if my balloon expands past a certain stretch distance, then these welds will break. And the threshold that worked for me was 0.0075. Usually this value is a bit fiddly, but that's what worked for me. Next, to inflate this, we need a bit of pressure, so let's do that using a vellum constraint again, which will set up to be a pressure constraint. And to set this up, I'll need to do a few things. On the one hand, I could, of course, create this pressure here from the individual pieces' connectivities, resulting in my case 36 individual pressure constraints. However, I want a single constraint for the whole geometry, so to do that, I'll instead use define pieces from attribute, and I'll have to create this attribute. So after the edge fracture, I'll drop down a point wrangle, goes in here, and I'll just set an integer attribute called class to be 1. So all of these individual points rest in the same class, which is already set up in my piece attribute name here in the vellum pressure constraint. Let's just scroll down here and enable the output group, which I'll call p-stretch for pressure stretch. Alright, almost done. Let's, in our case, drop down a dot net, wire in the geo in the first and the constraint geometry in the second slot, and dive in there. So in here, I'll use my vellum solver to simulate the whole thing, wire this to my output, set my constraint iterations to 24, and in my second, my advanced tab, I want to scroll down here and go to disable broken welds, which is usually unchecked, and the default behavior is as soon as welds break, the points that had been welded together will get pushed apart a tiny bit to prevent intersections and penetrations. In our case, I found it working better with this behavior disabled, but that might be different from use case to use case. In my case, I had better results, leaving this checkbox checked here. Next, we'll need a vellum object, which will feed into the solver here. And now let's build the interaction and logic for the simulation. And I'll drop down a few nodes here. So I'll just use a merge wired to the post-solve input of the vellum solver. And the first thing I wire in here is the vellum constraint property node, which in my case I want to restrict to a group, namely the p-stretch, that's the pressure. And to inflate my balloon, what I'll do is I'll animate my rest length scale from 1 on the first frame, so keyframe that. And then in my case, I went to a later frame here, opened up my animation editor, and keyframed this to a value of, say, 200. There we go. Let's just make this a linear animation like this, and reset our simulation. So when I simulate this now, I can see my balloon inflating, so that's working, and also there's some braking happening. However, what's still active is my pressure constraint, so these pieces will get pushed further and further, even though they're broken. So what we need to do now is find a way to check if those welds had broken, and if they did break, disable the pressure constraints. When we middle mouse on the Vellum solver, one thing that caught my interest is this broken points group. However, most ways to access this weren't successful, and my speculation is that this is only an internal group which gets reset after each simulation step. And about the only way to access this is on this post-solve slot here with a slight hack. So I'll use a geo wrangle, which I'll drop down there, goes into the merge. It's set up to run over the geometry and only over the broken group. And in here, I'll extract this broken group attribute. So basically I will set a detail attribute on my geometry, which I'll call broken, and I will set it to 1 if there are any points in the group broken. And that's how I extracted this temporary group that's only available to the Vellum solver usually. And now what I can do is drop another geo wrangle, set this one to be primitives, and bind it to the constraint geo. But also I want to bind my normal geo, and if you're forgetful like me, you can use the Vellum constraint property, the bindings, and the inputs tab as a cheat sheet. So in the inputs tab, I'll just copy this dop data here, and remember to set my first input on myself and the second input to dop data. I'm going to do that for my geo wrangle. First input is myself, second is the dop data with this dop data path here. So now on my slot 1, I can access my normal geometry in contrast to my constraint geometry, which I bound to my 0 slot here. So I'll check for broken. So I'll load the detail attribute from my normal geometry, called it broken. And then I will check if broken set to 1. And if it was so, I will remove my primitive that I'm currently working on. And I want to do this only for the pressure constraints, so only for the P stretch group. That goes in here. Let's save this, and for the points, maybe let's just copy this detail attribute and be proper about this, so when we initialize our points, let's here also initialize our broken attribute, which will initialize to 0, like this. Okay, highlight the .NET, fingers crossed, and hit play to simulate this. And you can see what's happening here. As soon as the first holes break here, the pressure constraint is deleted and the whole sphere collapses into itself. However, this is really abrupt and the whole sphere does not really shatter, because as soon as the first holes appear, as the first welds break, pressure constraint is not enforced anymore and the whole thing just collapses. So there's no chance of further tearing there. And to drive this a bit better, to control this a bit more intricately, I came up with a second way of checking broken welds, where I can actually dial in how many welds should break before the pressure constraint gets deleted. So let's build that by going up 1 level, just copying this whole node tree that we just built, and I'll just disable my original node tree here and dive into the second node tree, and we're going to modify this setup. So in my initial point wrangle, for this setup I won't be needing a detail attribute called broken, so let's just delete that for clarity. And my plan here is to check how many primitives are in this weld group here, so in this weld bend group. Because if they break, they get deleted. So during the simulation, the number of active weld constraints will differ from the original number of weld constraints. Let's just save the original number of weld constraints using a primitive wrangle, which I will wire in my constraint stream here before feeding it into the .NET. And oh, I'm realizing I do not need to run this over primitive, but I can run this only once. And I'll create an integer attribute called nc, number of constraints, and we'll use the n primitives group function to determine how many primitives are in that weld bend group. And we're working on our 0 geometry like that. So we determined this number of primitives in here. Let's write it out as a detail attribute. Let's call it orig.nc, original number of constraints, and should be equal to the integer we just calculated. So let's head to the geo spreadsheet, go to details, and we can see we've got 387 constraints. Good, let's highlight the .NET, go in there, and the first thing I want to do is take this first geo wrangle and change the bindings, so I'm running on constraint geometry. And in here, this only needs to run once, is not restricted to any group. And in here, I want to find out my number of constraints in this current simulation step. So again, let's just delete all this and go up 1 level and just copy this node's code here back into my geo wrangle, paste it here. And I want to create another detail attribute, this time call it nc, for number of constraints, which I'll later compare to my original number of constraints. And let's also be nice and initialize this value before the simulation. So again, head up into this primitive wrangle, just copy this line here, and initialize my number of constraints with the same number of original constraints for the first step, like so. Back into my .NET. Second thing I'll do in my GeoWrangle here is again check my data bindings. So it's set to constraint geometry and limited on my p-stretch, that's my pressure group. So instead of checking if it's in the broken detail here, instead I'll again load up my number of constraints attribute that I just wrote out in the wrangle previously. Let's copy this line and do the same thing for my original number of constraints attribute, so orig_nc. And then in my if statement, I want to check if nc is not equal to original nc, orig_nc like this, and that should be it. So this is a really coarse check, so I'm just checking if my number of constraints changed to my initial number. Let's just save this and run the simulation briefly, which totally did not work. Okay, let's check what happened here. Yeah, and what I messed up here in the first geometry wrangle, when I set up my data bindings, I set it to constraint geometry, but didn't check the inputs, so let's just do that and set the first input to myself, no reads of outputs, like that. And that should do it. Okay. Now, you might say this didn't change much, and that's right, because we're just checking if the first weld breaks. So let's get back into our code here. Let's reset the simulation. And instead of just simply checking if my number of weld constraints changed, let's check if the difference between the original number of constraints and our current number of constraints is bigger than a threshold, for example 50. Let's resimulate. And you can see now we can control how many constraints should break before the pressure constraint is eliminated. And maybe let's add a slider to this. Call this one number of welds to break. And now we can dial in any threshold number that we'd like. To dial in the look of that tearing and this balloon popping and breaking apart. So those are two methods of determining if any of your welds broke and using that info to further drive the simulation, in this case, removing another set of constraints. As always, intrigued to see what you guys come up with, and until next time, it's cheers and goodbye.